All right, kiddos, so this is going to be our lesson 4-3 video for Algebra 2. So in it, we're going to discuss further absolute value functions and their transformations. And if you remember from geometry, transformations, and also in Algebra 1, transformations is just basically how figures can change in space, right? So this is no exception. It's the same idea, exact same idea. But first, we're going to review what are the number sets and what letters represent them. Okay, so if you forgot all of this, and you probably haven't seen this since 8th grade or 7th grade, depending on when you took pre-algebra. So starting with the most basic, which is your natural numbers. You'll hear these called the counting numbers. And that's the simplest way to remember them. You may also remember in 8th grade or 7th grade, you had something called whole numbers, right? The whole numbers were 1, 2, 3, 4, 5, and so on. Well, the natural numbers is what you're actually going to see later on in higher math. So that's what we're going to talk about. Natural numbers are so starting with 0, and then your positive integers after that. So your positive whole numbers after that. So 0, 1, 2, 3, and so on. Okay. Integers include the natural numbers, obviously, right? That's why they're circled in with them. Integers include the natural numbers, but they also include their negative counterparts, right? So we can say 0, 1, 2, 3, so on, so on, so on, but we can also go back the other way, -1, -2, -3, and so on. Okay? Then we get into rational numbers. I'm starting to run out of colors to use here. Let's see if I can find a more vibrant green than that one. Well, we'll use blue. So rational numbers. Rational numbers are any numbers that can be written as a fraction. So the number 5, for example, and that's not showing up very well. The number 5, for example, I'll use red. The number 5, for example, can be written as just the whole number integer 5, right? Or we can say it's 5 over 1. We can say 25 over 5, and so on. It can be expressed as a fraction. We can also say that about the number 1/3, 3/4, -3/4, -1/2. I mean, millions of examples. Well, an infinite number, really. Okay, then we will get into the, and here, I think white will show up on here. We'll get into the real numbers. Okay, so real numbers are all the numbers that you have ever learned about so far. Okay, all the numbers you've ever seen so far are real numbers. But before I get into that, let's talk about, I'm running out of colors here. Maybe black will show up okay. Let's talk about irrational numbers. So irrational numbers are numbers that cannot be written as fractions, right? So they cannot be expressed rationally. So these are numbers like your weird, ugly decimal square roots, like the square root of 2, square root of 3, square root of 5, 7, square root of 10, on and on and on. But these also include your really popular constants like pi, the natural base, Euler's number, and many, many, many more, like Planck's constant, and I can continue on and on forever. But these are all numbers that cannot be expressed as a fraction. Okay, so now all of those numbers you've ever learned are incorporated into the real number set. So anytime you see, like, for example, when we're talking domain and range, an x such that x is an element of R, right? We're saying that x is pretty much capable of being any of these numbers in here. Okay, any of these numbers that you've learned about so far. So that includes your irrational numbers and your rational numbers, which of course also includes your integers and your natural numbers. Okay, so now we're getting out into, and now I'm really running out of colors. Now we're getting out into the numbers we haven't learned about yet, but we will learn about soon enough. So let me figure out what color I want to use. I guess I'll just use black again. So complex numbers and imaginary numbers. So imaginary numbers, we'll learn about those here later. But basically the imaginary number, there's only one. It's called I, and it's the square root of -1. We'll learn about that in greater depth later on. And then complex numbers are numbers written in the form a plus b times I. Okay? And I'm not even going to get into what that means just yet. Like I said, later on in this course, trust me, we will go way far in depth into what complex and imaginary numbers are. Okay, so into our actual transformations, right? So we needed to have that review just so that we could understand basically just set notation. Okay, so this is the real big part of the lesson. Really simple, right? But this is where we start doing what I call functional analysis. So we analyze functions, right? And the first kind of function that we're going to analyze is the absolute value function. Okay, so this right here is the parent function of the absolute value function, meaning it's the most basic of its type. Okay, so if we assume every function comes from a family, right? In each family, you have the most basic type, namely the parent function. Okay, so anytime we transform or change the parent function, it's going to basically be able to be expressed this way. Okay, so A, let me try to color code. So A is our vertical stretch or shrink, but it also gives us a reflection across the x-axis. Okay. B is the horizontal stretch or shrink. We'll talk about what all these mean here in a second. Trust me. C is our horizontal translation, meaning we're going to shift left to right. And D is our vertical translation. We're going to shift up or down. Okay, so this is the point at which in class you would do this with me. But in the video, I'm just going to make do and try to do the best that I can. So let me try to minimize this guy. I didn't mean to do that. Let me bring this guy over here. Okay. So let's answer these questions one by one. Make that more viewer friendly. Okay, so we're going to go through and answer each one of these questions. I think it's 10 of them. Oh, good Lord, that's okay. I can't make that any smaller. But let me see. There, I'm going to make my graph a little bit bigger, I guess. Okay, so let's answer number one. What happens as A increases or decreases? So that's our A. That's our A that we talked about here. Our A is our vertical stretch or shrink, right? So what happens when we increase that? So if I use Desmos and increase the slider, well, we see that we're getting vertically stretched. Okay, so when A increases, we get vertically stretched. When A decreases, we get vertically shrunk. Well, until we get to zero, right? Then when we get to zero and past zero, then we see we get a reflection. Okay, so that lets us answer number two. So what happens when A is in between 0 and 1? Well, let's see. So when A is in between 0 and 1, so basically when A is a fraction, right? We see that we are being, you can call this vertically shrunk, or you can call this horizontally stretched. Okay, and I know that's going to be confusing later on, but trust me, we're going to get practice here. Okay, what happens when A is less than 0, when it's negative? Well, that's when we see that we get a reflection across the x-axis. Okay, so when A increases, we get vertically stretched, right? When A decreases, we get vertically shrunk or horizontally stretched. When A is a fraction, right? When A is a fraction, we get horizontally stretched or vertically shrunk. Okay, when A is less than 0 or negative, that's when we get reflected across the x-axis, and then it behaves much the same way, just on the other side of the x-axis. So now let's talk about B. So I'm going to set this back to 1, if it'll let me. No, not -1. I'm going the wrong way. There we go. So now let's look at B. Okay, so B is our horizontal stretch or shrink factor. And we see it virtually does the same thing that A does, right? It either vertically stretches or vertically shrinks. But what do you notice about if it's positive or negative, right? It doesn't cause a reflection across the x-axis. And that's because B is inside of the absolute value brackets, right? Which means it doesn't matter if it's positive or negative, okay? It's always going to be a measure of magnitude. Well, what happens when B, so that answers number 5 also. So we answered 4 and 5 in one shot. So the sign of B, does it matter? No, it doesn't matter. What happens when B is a fraction? So when B is a fraction, we see much like with A, when B is a fraction, we get a horizontal stretch or a vertical shrink, however you want to refer to that. Okay, they mean the same thing. So let me reset this guy back to 1, back to the parent function. There we go. Okay, so now let's see what happens with C. Okay, and again, C is supposed to be our horizontal translation right here in green. Right, so let's see what happens when we mess around with the slider for C. Okay, so as C increases, we see that we shift to the right. We translate to the right that many units. So when C is 0, we're at x equals 0. When C is 2, right, guess where we're at? We're at x equals 2. Okay, so this is obviously our horizontal translation. Okay. Now, this can be confusing, okay? So when C is equal to 2, because that's what we saw, right? So here's our x, y-axis. So our parent function, and I'll do that one in yellow, our parent function has our vertex right here, right? So this would be f of x is simply the absolute value of x, right? And if I do a transformation of that, namely g of x is the absolute value of x minus 2, well, that's going to shift me 2 units to the right now. It's going to look exactly the same because there's no horizontal stretch or shrink or anything crazy like that. But I went from 0 and I went 2 units, right? I went 2 units to the right. And that may seem counterintuitive because that says minus 2. But if you have a minus 2, right, we're going to go 2 to the right. If we had instead, let's say, h of x is equal to the absolute value of x plus 2, well, you can already guess this is going to shift us 2 units to the left, right? And again, it's going to look exactly the same. There's no horizontal stretch or shrink or anything, right? But it just was shifted 2 units to the left. Okay, so that can get confusing just because of the positives and negatives that occur there. Okay, so number 9, we're talking about D. So D is our horizontal, or not our horizontal, our vertical shift, right? So let me reset my C back to 1, or actually it was at 0. Let me put it back at 0. So what happens when we shift D up and down? Well, our function itself shifts up and down, okay? And this is analogous to y equals mx plus b, right? The plus b is our y-intercept of of a linear function in slope-intercept form, right? So this is the same idea. So if I say d is positive 4, well, guess where my y-intercept is, right? And I shouldn't say y-intercept because, well, what happens if I also shift to the right by 2, right? So my y-intercept is not 4, but my vertex went up by 4, okay? So that's where we have to be careful. So I shifted to the right by 2 and up by 4. So what would that look like as a function? So let me erase some of this here. I'm going to be careful not to get too crazy with the eraser. Okay, so I'm going to keep some of this here. So I'm going to use pink again to illustrate my g of x, my transformation. So let's say I shifted 2 to the right, so that would be x minus 2 inside the absolute value brackets. And I also shifted up by 4. So I would also come up here. So that just means my vertex is going to be here at 2 by 4, right? Because I went 2 to the right and 4 up. And then my graph is just going to look exactly the same, right? It's just been moved. It's been translated, okay? So that's all there is to it as far as transformations. We're obviously going to have to play with it a lot more than what I showed in the video, right? But that's the gist of it. So if you have any questions or any concerns or anything, obviously shoot me an email or let me know in class. Otherwise, that's the end of this video. Goodbye.